In this lesson, we continue with our discussion of rational expressions. In the previous lesson, we just looked at rational expressions in general, which is the idea of a polynomial divided by another polynomial. Now we're going to take a look at mathematical or arithmetic operations, and we're going to be focusing on multiplying and dividing rational expressions for this lesson. In order to do that, a quick review, hopefully unnecessary for many of you, but just in case some of you need a reminder here, what to do just when you're multiplying or dividing fractions in general. So the first thing to keep in mind is when we have multiplication, the way you do multiplication is you multiply the numerators together and you multiply the denominators together. Another way of expressing this then would be 1 multiplied by -3 all divided by 2 times 5. 1 times -3 is of course just -3. 2 times 5 is equal to 10. There were no common factors between numerator and denominator, and so this is the answer I ended up with. Moving to my second example, this one can be written as 50 times -3 over 27 times 5. And in this case, we could go to this next step. We could say, well, that's -150 over 135. But that's actually not an ideal way to do this. I don't recommend that. Whenever possible, I suggest you get rid of common factors as soon as you can identify them. And you might do this in multiple steps. So in this case, we recognize the number 50 and the number 5 have something in common. 5 goes into 5 once, and 5 goes into 50 10 times. We can also see that the number 27 and 3 have something in common. So 3 goes into 3 once, and 3 goes into 27 9 times. Depending on how you write these things, you might actually want to write it this way as well. You might want to get rid of that whole bracket and say 3 goes into -3, -1 time, and then it goes into 27 9 times. That's up to you. That's just a style difference. Choose whichever one of those allows you to write things most clearly. So now we get 10 times -1, which is equal to -10, and 9 times 1 is 9. When you get to this step, always take a second look and make sure you haven't missed any common factors. In this case, it's pretty obvious that there's nothing these two have in common, so this is my final answer. Also, technically, we don't need to combine these things. When you have multiplication like this, you don't have to go to the combination step right away. You could have recognized that 5 goes into 5 once and it goes into 50 10 times. 3 goes into -3, -1 time, and into 27 9 times, and then just do this in one step, and you end up with -10 divided by 9, which of course is what we got the first time through. Now with division, I actually don't recommend you try to do it all in one step. I strongly recommend that at the very least, you write out your first step, which is to use the rule of division. When we have a fraction divided by another fraction, we're actually going to turn that into a multiplication problem. And what we're going to do is we're going to multiply that. I'm going to do it using brackets. I'm going to take the first fraction, and I'm not going to change it. I'm going to multiply by the reciprocal of the second fraction. So dividing by 20 over 15, which means I'm dividing by this whole thing, is the same thing as multiplying by 15 over 20. And now that I'm at this point, I could combine these, but it is just as clean to now take a look between numerator and denominator. We actually could have done it even sooner in this case. Between numerator and denominator, I see that 5 goes into 15 3 times, and it goes into 24 times. And now that I've done that, this is going to be one of those ones that has multiple levels of common factors. 4 goes into 4 once, and 4 goes into 12 3 times. Then we could say that 3 goes into 3 once, and 3 goes into 27 9 times. And then finally, and of course you don't have to keep switching colors, I'm just doing that so you can keep track of what I'm doing here. 3 goes into 3 once, and 3 goes into 9 3 times. So if I were to do that all in one step, I end up with 1 times 1 over 3 times 1. Why did I write a 3 in the numerator? 1 times 1, which is 1, over 3 times 1, which is 3. Now, if that's too much, or maybe you don't see it all in one shot, so let's back that off to the point where maybe we recognize something like, let's say, one more back off here. There we go. And so we get to this point and we say, okay, that looks good. 3 times 3 is equal to 9. And then 27 times 1 is 27. And now you take another look and you recognize, oh, hold on a second here. 9 goes into 9 once, and 9 goes into 27 3 times, which gives us a final answer of 1/3. We could have also looked at it in looking at common factors. For example, 12 and 27, well, the number 3 goes into 12 4 times, and the number 3 goes into 27 9 times. And then 20 and 15, 5 goes into 15 3 times, and 5 goes into 20 4 times. But at this point, I would actually write out the new product of these fractions. So this one would be 4 over 9, and I would multiply that by the reciprocal of this one, which would be 3 over 4. And then we end up with 4 goes into 4 once, and 3 goes into 3 once and 3 times, and of course we end up with 1/3. Now remember, I'm just doing this to refresh your memory, to give you some tips on how to do this, but the goal here is to do this with rational functions. So what are the steps we're going to want to go through? Now, because we're going to be dealing with rational functions, that means the numerator and denominator are often going to both be polynomials. You're going to want to completely factor all numerators and all denominators independently of each other. So there's your first step. The second step is to perform the mathematical operation in question. That's going to be particularly important if we're doing division. Okay? For multiplication, as I pointed out, you can do your common factors with multiplication quite easily without actually performing the operation. But with division, it's quite important. Restrictions. Where could I have a denominator equal to 0? This is particularly important if you're going to be dividing out any factors, because if a division by 0 disappears, you can't afford to lose that information. And so identifying where any denominators could be equal to 0, stating your restrictions, allows you to then divide out common factors and then simplify if possible. So the rest of this lesson is really about doing some examples that look like this. Over to the side here, you can see I've got the same steps we just looked at there. So let's take a look at this one. The first thing we're going to do, factor the numerator and denominator separately. They are already factored. This next step is optional because this one's multiplication. This x is in the numerator, this x squared is in the denominator. I recognize that I can take common factors out of those, but let's go ahead and perform the multiplication, and I end up with 12x squared over 4x. Identify restrictions. Where could any denominator be equal to 0? In this case, I end up with a restriction that says that x cannot be equal to 0 because I have an x in the denominator. So x equals 0 would cause division by 0. And now I can go ahead and do my factoring. The number 4 goes into 4 once, it goes into 12 3 times. The factor x to the power 1 goes into x 1 time, and it goes into x squared, leaving behind an x to the power 1. Now that's a tougher one for people. X over x squared. Just remember that that's the same as x over x times x. The x's divide out, leaving me with 1 over x in the end. So my final answer here is 3 times 1, which is equal to 3, over 1 times x, which is simply equal to x. And this restriction, just for good communication, I might bring that down and say where x is not equal to 0. based on our previous lesson, the fact that we divided out x over x, that's this part right here. So the feature that would create would be a whole, except for the fact that there's still an over x still there, which would be a vertical asymptote. So in this case, when there's both, there seems to be an indication of both a whole and a vertical asymptote, the vertical asymptote is going to win. Okay? So the vertical asymptote, if you like to think of it this way, the vertical asymptote is a more powerful restriction than the whole. Or another way of thinking of it is, we don't have to consider a whole there because the vertical asymptote is going to prevent us from going anywhere near that spot on the graph anyway. Okay, so now we have division. So as I recommended before, the first thing it says is to factor the numerator and denominator separately. And so in this case, they're already in a fully factored form. You could actually interchange steps 1 and 2. You have some options about even steps 1, 2, and 3. Well, you need to wait for 3. But 1 and 2, you can choose the order there. In this case, negative 5x cubed over 3y. But I'm going to change that to a multiplication. So that's going to be multiplied by 25x squared over y. And now that I've done this, I'm not going to perform the mathematical operation. I've performed the mathematical operation here on the division, but now that I have multiplication, I'm simply going to look for common factors between the numerator and denominator. And I specifically chose this one. When you first look at this problem, you might have thought, oh, 5 and 25, y and y, x squared goes into x cubed. I've got lots of things that I can divide out there. But it turns out, if you follow this, if you're careful about this, when we turn this division into a multiplication, there's actually nothing for us to divide out here. So now we just have to go ahead and do our numbers on the top, which is negative 125. X cubed times x squared is x to the 5th, over 3y times y is 3y squared. Since I didn't divide out any factors here, I'm not going to lose any information. But now I have to, and I really need to emphasize this, this is the first time we're running into anything that looks like this. We have to identify restrictions where any denominator is equal to 0 or potentially equal to 0. So in this case, we have a restriction that says y is not allowed to be equal to 0 because it's in the denominator here. But when we first were presented with this expression, 25x squared was in the denominator of this second factor, this thing that we're dividing by. So that also gives a restriction that says x is not allowed to be equal to 0. And that's a pretty easy thing to miss. And that's why I really emphasize this, any denominator equal to 0. So at any point in time, as you work through the algebra here, anytime a variable ends up in the denominator, you have to place a restriction on it that it's not allowed to be equal to 0. Okay, now this one actually gives us an opportunity to do some factoring to start. In the first term here, the first factor in the numerator, I can take out a common factor of 2, leaving me with x plus 2. The denominator is actually a difference of squares, so I'm going to write that as x minus 3, x plus 3. You might combine these steps, but right now I'm not going to take any chances, so I'm going to write this out as x minus 2, x plus 2, all divided by, and now this one is a simple trinomial, two numbers that multiply to give negative 3 and add to give negative 2. And that's going to be x minus 3 and x plus 1. And then from here, I can perform the mathematical operation. So that's 2 times x plus 2, all divided by x minus 3, x plus 3. And now I'm going to convert this into a multiplication, which means I'm going to take the reciprocal of this second fraction and write it as x minus 3, x plus 1 over x minus 2, x plus 2. And I'm just going to throw this out. I just happened to be reading something this morning along these lines. It's all well and good for you to watch me do this, whether it's in class or in this video or both as you're brushing up on things. You have to practice these things. You can watch me do this and it can all make sense, and then when you try to do it yourself, whether in your homework or more importantly on a test, it falls apart on you. Usually, there are a number of reasons why that can happen, but the biggest reason why that could happen is you have not practiced this. You need to be able to practice this without referring to your notes, without referring to the video or any other kind of resource, without asking for help. If you can't do that on your own when you're practicing, how are you going to be able to do that on your own when you're being tested on it? And I'm not talking about doing it once. I'm talking about doing it a half dozen times, a dozen times, perfectly every time. We learn these steps and we repeat these steps so that when we practice them, they start to make more sense and we don't make mistakes on them. Sorry for that little speech there, but I felt it was necessary to inject that into the conversation here. Okay, back on track. I've factored things. I've performed mathematical operations. I should now take a look for common factors. So I'm going to show you doing the order a little bit differently here. With greater understanding here gives you a little bit more of an option on how you can do these things. If you're uncertain, just follow those steps exactly the way I provided them. So now I'm going to take a look for common factors. So between the numerator and denominator, there's a common factor here of x plus 2. There's a common factor here of x minus 3. X plus 1, x plus 3, x minus 2, and the number 2. That's it. So I've got all the common factors have been divided out, and that's going to give me 2 times x plus 1 over x plus 3 times x minus 2. But now I have to write my restrictions. Any value of x that appeared in the denominator is going to form, any variable that appears in any denominator is going to form one of the restrictions. This is one of the reasons why we factor early. So I started with, here it's still written as a division, so I'm going to look at all the denominators here. That is a restriction on x cannot be equal to 3. This second one, so there's our first restriction. Second restriction is that x cannot be equal to negative 3. This third one is the same as the first one. So here is our third restriction, which is that x is not equal to negative 1. And then when I took the reciprocal of this term, I ended up with x minus 2 and x plus 2. So now here is my fourth restriction, which is x is not equal to 2. And I have a fifth restriction here, which is that x is not equal to negative 2. Now let's take a look. Well, first of all, let's go ahead and write these out. I could write them out as a list. I could also write them in a slightly more condensed form. X is not equal to plus or minus 3, because I have both a plus 3 and minus 3. X is not equal to plus or minus 2. And x is not equal to negative 1. And as a last exercise here, I want you to consider which of these is going to represent a whole versus a vertical asymptote. And the easy way to know that is we take a look at the final form. Those are vertical asymptotes. So x plus 3, which gave me this restriction, x not equal to negative 3, that's a vertical asymptote. X minus 2, which gave me this one. The rest of them, which have been, let's see, x, where are we? X plus 2, that means that x minus 2 is going to be a whole. That was divided out. And what else do we have? X plus 3, no, that went away. So that means x minus 3 is a whole. And this last one is a little bit confusing, because it was a vertical asymptote in the original, but it's not going to result in a vertical asymptote on this graph. And so it actually is also going to be a hole. Basically, you identify the vertical asymptotes first, and then any other restriction is a hole on your graph. All right, now this one, I've got a note over here on the side about order of operations. The order that you do division and multiplication is the same. But when you have two operations that have, it's known as precedence, when you have two operations with the same precedence, you evaluate those operations from left to right. So we're going to do everything the same to start. Let's start by factoring. I'm going to factor out a 3, and I have an a plus 2 over 9a squared divided by a plus 2 over negative 3a multiplied by 15a over 2. Now we have to do these in the correct order, and that means that the first operation is going to be this division, and the second operation is going to be this multiplication. We use parentheses to visually identify that. That is what's going to force that division to occur first. So it might be tempting to take a look. 3 and 15 have common factors, a and a. So you might be tempted to do something here. You might be tempted to do something to divide out common factors there, but that is not permitted because we have to deal with this division first. And by doing that, we end up with 3 times a plus 2 over 9a squared. And now we have a multiplication by negative 3a over a plus 2. And that will be followed by 15a over 2 as a multiplication. So this is still what we do first. But now, since they're all multiplications, we end up just with this combined numerator and the combined denominator. So we can actually now remove common factors from any numerator along with any denominator. So for example, I take a look at the number 3. 3 goes into 3 once, and it goes into 9 3 times. 3 goes into 3 once, and it goes into 3 one time. I have, let's switch over to, do I have anything else for numbers? I do not. Switch over to green for the variables. A goes into a once, and it goes into a squared, so that there's a to the 1 left over. A plus 2 goes into a plus 2 once, and it goes into a plus 2 once. And so now, and you have to be careful, don't be scribbling things. Make sure you're doing this cleanly. Looking across in the numerator, I have this negative sign. 1 times 1 times 1 times a times 15. So this is going to be negative 15a, all divided by, everything here looks positive. There's a 2, and you can see there's an a. So I actually missed my common factor of a there. I actually realized it as I started to collect things together, but that's okay, because it's never a problem if you see something like this happen, and then you write your correct final answer in another step. There is absolutely nothing wrong with that. We're now going to go back. We're going to take note of our restrictions. So what are my restrictions here? I start off with my original expression. I might do it here, or I might do it here. It's probably a good idea to do it in the factored form, although it doesn't make any difference in this case. I have an a in the denominator, so that gives me a not equal to 0. I have an a in the denominator, well, that's already taken care of. And then when I take the reciprocal of this fraction, I end up with an a plus 2 in the denominator, which means that a is not equal to negative 2. And so now I have these restrictions: a not equal to 0, a not equal to negative 2. And when we ask ourselves the question about asymptotes versus holes, you can see my final form doesn't have any of these factors present, which means that both of these restrictions on the graph would be expressed as a whole. They would be expressed as some kind of, well, in this case, this is a horizontal line, and it would have a hole at 0 and a hole at -2. I'll just put that on. So this is essentially y equals -15 over 2. The only difference is I'm assuming that this is a y-axis and the a-axis, because remember our variable was in terms of a. Okay, that's it. Relatively straightforward lesson. The key to this one is not conceptually heavy, it's just the algebra. You need to practice this algebra. I have a bunch of questions here that I've assigned, but there are plenty of other questions in this same section that you can look to for additional practice, or you can ask me if I can generate another worksheet for you.